A massive stone block stands abandoned in a quarry, a silent challenge from the ancient world. The stone quarries that hold the secrets of impossible construction are not just empty pits. They are the archives of lost engineering, containing the untold stories of how our ancestors achieved the unthinkable. By the end of this, you will see history not as a simple timeline, but as a tapestry of brilliant, forgotten solutions. We will journey from the half-carved obelisks of Egypt to the mysterious Moai of Easter Island, decoding techniques that defy logic. How did they move 1,000-ton stones without modern machinery? What knowledge was left behind in the rock? The true scale of ancient ambition is waiting to be uncovered. Are you ready to question everything you thought you knew about the past? These silent landscapes are scattered across the globe, a ghostly network of ambition frozen in time. From the sun-baked granite quarries of Aswan in Egypt to the high-altitude andesite pits of the Andes, the evidence of ancient megalithic projects is written into the earth itself. In Aswan, an unfinished obelisk lies trapped in the bedrock, a single piece of stone that would have weighed over 1,000 tons. Had it been freed, it would have been the heaviest monolith ever attempted by the ancient Egyptians. Far away in South America, at a site like Rumacolca, the Inca were quarrying andesite, a volcanic stone of immense durability, to build their precisely fitted walls. Even on a remote Pacific island, the quarry at Rano Raraku is home to nearly 400 Moai statues in various stages of completion, some still attached to the living rock of the volcano. Why were these specific locations chosen? It was far more than simple convenience. As expert geologist Dr. Aris Thassos explains, the selection of stone was not arbitrary. It was a profound understanding of material science. These cultures sought out the very best rock for their grandest projects, granite for its crushing strength, andesite for its resistance to weathering, and volcanic tuff for its relative ease of carving. This reveals a universal first step, a shared geological intelligence. They were not just moving mountains, they were listening to them, understanding their faults and their grain. The scale of these quarries speaks to an operation spanning generations, a sustained effort that required a staggering command of logistics and labor. How did cultures separated by oceans and millennia all arrive at the same monumental conclusion? What fundamental principles of engineering and human organization did they discover independently? The stone itself is only the beginning of the mystery. The unfinished obelisk of Aswan is a stark reminder that even the greatest builders were not infallible. Carved directly into the vibrant red granite, this colossal shaft remains imprisoned by the bedrock it was meant to crown a temple. It stretches nearly 140 feet, a length that would have made it the single largest obelisk ever erected by the Egyptians, a needle of stone piercing the sky. Yet it was never freed. Its surface is a chaotic landscape of tool marks and, most tellingly, a catastrophic crack that snakes along its length. To shape this behemoth, workers used nothing more than balls of dolerite, a stone harder than granite. For months, perhaps years, they would have pounded away, pulverizing the granite bit by bit in a relentless, deafening rhythm. The logistical challenge of moving such a monolith was another puzzle entirely. Once freed, this 1,000-ton giant would have needed to be loaded onto a massive sledge, dragged to the Nile, and floated on a barge of unimaginable size. Its abandonment raises profound questions. Was it that fatal crack appearing deep within the stone that forced the architects to walk away? Or did a pharaoh die, shifting priorities and funds to a new project overnight? This failure is ironically one of our greatest windows into their success. It shows us the sheer audacity of their plans and the physical reality of their methods, frozen in time. This cracked monument teaches us more than a perfect one ever could. It reveals the razor's edge these master builders walked, where a single flaw in the stone could undo generations of work. Far to the north of Egypt, in Lebanon's Bekaa Valley, another quarry holds an even greater enigma. The Roman temple complex of Baalbek stands upon a foundation of staggering proportions, built with the largest known worked stones on Earth. Lying in a nearby quarry is the most famous of these megaliths, the Stone of the Pregnant Woman. This single block of limestone is a true behemoth, stretching over 64 feet in length and estimated to weigh more than 1,000 tons. To stand before it is to feel a profound sense of disbelief. The scale is simply not human. Its surface is perfectly smooth, its edges sharply defined, a finished product abandoned and waiting for a journey that never began. And that journey was a formidable one. The quarry sits nearly a full kilometer away from the temple platform. So how did the builders intend to move a block heavier than 3 fully loaded jumbo jets across such a distance? The proposed methods stretch our understanding of ancient engineering to its absolute limit. Some archaeologists point to the Romans' advanced use of cranes and winches, powered by massive human treadmills. Yet, even the most sophisticated Roman crane could only lift a fraction of this weight. The more widely accepted theory involves an immense system of earthen ramps, rollers, and brute manpower. Imagine an army of thousands straining against ropes thicker than a man's torso, inching the stone along a carefully prepared road, a process that could have taken many months. But here is where the mystery deepens. The foundation at Baalbek that these stones were meant for is actually older than the Roman temples above it. This has led to a fierce debate. Were the Romans truly the original builders of this cyclopean platform, or were they building upon the ruins of a much older, perhaps even more advanced civilization? The precision of the stone's carving and the audacity of its scale defy simple explanation. It pushes the boundaries of what we believe was possible, forcing us to reconsider the capabilities of ancient engineers. What organizational genius could command the labor, the resources, and the sheer will to attempt such a feat? The stone does not answer, but its silent presence in that Lebanese quarry asks a question that echoes through the centuries. High in the Peruvian Andes, the air grows thin and the mountains challenge every step. Here, at the fortress of Ollantaytambo, the Inca built with a precision that seems to defy both gravity and time. They used massive blocks of pink rhyolite, a stone harder than granite, and fitted them together so perfectly that not even the thinnest razor blade can find a gap. This was not a simple stacking of rocks. It was a 3-dimensional stone puzzle engineered to last for millennia. To understand how this was possible, we must travel across the valley to the Cachacota Quarry, the source of this magnificent stone. The journey these rocks took is a story of human ingenuity written across a brutal landscape. The quarry sits high on a mountain slope, separated from the construction site by a deep river valley and a rushing river. How do you move a 200-ton stone down a near-vertical cliff face, across a powerful river, and then up the other side, all without the wheel, without iron, and without beasts of burden? The Incas had no pulleys or cranes. Their most powerful tools were bronze chisels, which are softer than the rock they were shaping, and harder stones used as hammers. Shaping a single block was a slow, deliberate process of pecking and grinding, a testament to immense patience, but the true magic was in the moving. They likely carved precise pathways and ramps into the mountainsides, greasing them with wet clay to create a slippery surface. thousands of workers would have coordinated with ropes made from native grasses, leveraging wooden logs as rollers and fulcrums. They understood the physics of friction and balance on an intuitive, practiced level. It was a symphony of controlled force, a communal effort where every pull and push was calculated. Once at the river, they may have diverted the water temporarily or built a massive causeway, dragging the stones across at the perfect moment. The final result at Ollantaytambo is a wall that does not just sit on the ground. It is interlocked with the earth itself, its foundations deep and its joints so tight that during an earthquake, the entire structure dances as one single, unified mass. The stones shift and settle, but they never crack or collapse. This is engineering that listens to the mountain. How did a culture without formal writing or blueprints achieve such a feat? It was a mastery born from generations of observing the land, a knowledge passed down through practice, not paper. They saw the strengths and weaknesses of stone and learned to work with them, not against them. This was not the work of slaves, but of a society unified by a common purpose, moving mountains together, one perfect stone at a time. But on a speck of land in the vast Pacific Ocean, a different kind of quarry tells a story of spiritual obsession. The volcanic crater of Rano Raraku on Easter Island feels less like a workshop and more like a sacred, frozen moment. Nearly 900 Moai statues dot the slopes, their blank eyes gazing from the living rock. Some are mere outlines, just faces emerging from the cliffside. Others stand fully carved, buried up to their shoulders in the earth, silent guardians of a forgotten ritual. These are not just heads, their full bodies extend deep underground, with elongated torsos and carefully etched hands resting on their bellies. They were carved from the crater's soft volcanic tuff, a stone that is firm enough to hold detail but soft enough to be worked with simple hand tools. The islanders used picks made of basalt called toki to chip and peck away at the rock, slowly releasing the giants from their volcanic womb. Each statue, some weighing over 80 tons, was a monumental investment of time and faith. Yet the greatest mystery begins the moment a Moai was freed from the quarry. How did a society with no metal, no wheels, and no large animals move these colossal figures for miles across rugged, hilly terrain? The most compelling theory suggests the statues themselves walked. Imagine teams of ropes with one group pulling from the front and others carefully rocking the statue from side to side. With each rhythmic tug, the massive stone giant would have been coaxed forward, inching its way across the landscape in a slow, deliberate wobble. This walking method would have required an intimate knowledge of balance and physics, a communal dance of immense skill. Another theory proposes a more straightforward approach, using a system of wooden sledges and log rollers, greased with sweet potato mash to reduce friction. This would have been a relentless grinding process, demanding vast quantities of timber, and this is where the story of the Moai takes a tragic turn. The very act of moving them may have led to the island's ecological collapse. Pollen samples from the island's soil reveal it was once covered in a lush palm forest. To transport the Moai, the islanders would have needed to cut down countless trees for sledges, rollers, and ropes. As the statues multiplied, the forest shrank until the land was barren and the soil eroded. The society that had the ingenuity to carve and walk giants across the island ultimately fell victim to its own ambition. The Moai are not merely statues. They are the physical manifestation of a powerful spiritual belief, a connection to ancestral spirits who watched over the living. What drove this civilization to pour all of its resources, and ultimately its future, into this single, monumental pursuit? Was it a desperate plea to the gods for survival, or the ultimate expression of a culture's identity? The silent, sightless Moai hold the answer, a stark reminder of the delicate balance between human ambition and the environment that sustains it. Deep in the sun-scorched eastern desert of Egypt, the Romans built a fortress of industry where no city should exist. Mons Claudianus was not just a quarry, it was a remote, sprawling complex dedicated to a single purpose: harvesting a unique stone for the glory of Rome. The granite here was special, a dazzling white speckled with black and purple crystals, prized for its beauty and immense strength. To extract it, workers faced a rock harder than almost any other. They could not simply pound it with stone hammers like the Egyptians. Instead, they drilled a series of holes along a predetermined line, hammering wooden wedges into the rock. Then they soaked the wedges with water. As the wood expanded with tremendous force, it would cleanly split the granite along a perfect seam. This method allowed them to carve out colossal column drums and blocks with surgical precision, often giving them a rough shape right there at the quarry to minimize the weight for the unimaginable journey ahead. That journey began with the most daunting leg. A finished column weighing 200 tons or more had to travel over 100 kilometers across the desert to the Nile River. How do you move such a load through sand and over mountains? The Romans built a dedicated, heavily reinforced road, wide enough for a massive sled and a team of oxen that may have numbered in the dozens. They likely used a system of capstans, giant winches turned by teams of men, to inch the sled forward. Progress was agonizingly slow, perhaps only a few miles each day. This was not a simple drag. It was a meticulously planned military-style operation, with way stations and guarded wells placed along the route. At the Nile, the stone was loaded onto specially built barges for the long voyage north to the Mediterranean, and then on to Rome itself. The granite from this desert outpost was destined for the empire's most iconic structures. You can still see it today in the Pantheon, its majestic columns standing as a direct line to this distant, arid quarry. But the stone is only half the story. The true marvel was the society that sustained this effort. Mons Claudianus was a fully functioning town, complete with barracks, bakeries, temples, and even a jail, all surrounded by defensive walls. 1,000 people or more lived here, from skilled stonecutters and blacksmiths to soldiers and bakers, all enduring extreme heat and isolation for years on end. They were supported by a supply chain that stretched across the empire, bringing in food, water, and wine from the Nile Valley. This was the Roman machine at its most efficient, a testament to its ability to project power and organize labor across impossible distances. It was a system built not on magic, but on sheer, relentless logistics. The next time you see a piece of ancient Roman granite, remember that its journey began in a silent desert, moved by the coordinated effort of thousands, all for the ambition of an empire that refused to be limited by geography. A massive block of stone sits in a quarry, presenting a seemingly impossible physical challenge. But what if the solution was not to break the stone, but to change its very nature? Legends from across the ancient world whisper of a different kind of secret, a lost knowledge that could make granite pliable. Stories from the deep Amazon speak of a mysterious jaguar plant, a rare vine whose sap, when painted onto rock, could soften its surface for carving. In Egypt, theories suggest that workers may have used vinegar or other weak acids to dissolve the crystalline bonds in certain stones, making them easier to work with simple tools. The idea is incredibly seductive. Instead of endless pounding with stone hammers, imagine an artisan gently molding a door jamb or a corner joint as if it were wet clay. It would solve so many of the logistical nightmares we have explored. But does this theory hold any weight under scientific scrutiny? Modern experiments have largely debunked the concept of a literal stone softening elixir. Granite and basalt are complex silicate minerals, and no known plant extract can significantly alter their hardness at room temperature. Vinegar, a weak acetic acid, has a negligible effect on such resilient rock. Mainstream archaeology firmly places these tales in the realm of folklore, not fact. Yet, the conversation does not end there. There are perplexing anomalies that keep the debate alive. At some ancient sites, including certain Inca structures, observers have noted stones that appear to be vitrified, as if their surfaces were once melted and fused together. Could this be evidence of an entirely different high-heat technique, or perhaps the result of a chemical agent that altered the stone's properties just enough to allow for precise molding? These fringe theories, while unproven, serve a vital purpose. They challenge our rigid assumptions about the past. Our modern minds are conditioned to think in terms of hard tools and brute force. We imagine armies of workers straining against ropes. But what if ancient science had discovered a simple, elegant principle we have since forgotten? A principle based on chemistry or acoustics that made the stone itself more cooperative. The search for a lost formula forces us to reconsider the very definition of technology. Perhaps the greatest secret hidden in the quarries is not a tool we can hold in our hand, but a recipe that was once common knowledge. The walls of these ancient quarries are not just scarred. They are inscribed with a permanent record, a language of grooves and pockmarks waiting to be read. Look closely at the granite in Aswan, and you will see surfaces dimpled like a golf ball, a texture created by the relentless pounding of dolerite hammers. Each small indentation represents a precise, calculated blow, a fragment of stone pulverized into dust. This was not reckless bashing. It was a methodical process of following the stone's natural grain, a conversation between the worker and the rock. Contrast this with the clean, linear chisel marks found in a Roman quarry like Mons Claudianus. Here, the evidence points to iron tools struck with heavy mallets to create controlled fractures. The tool marks are a direct imprint of the technology available, a timeline of innovation written in stone. By comparing these marks from Egypt to Lebanon to Peru, we can trace a fascinating evolution. We see the shift from the brute force of stone-on-stone pounding to the more refined leverage of metal tools, but the marks tell a deeper story than just the tools themselves. They speak of the people who wielded them, the consistency of the grooves, the even spacing of the strikes. These are the hallmarks of a skilled artisan, someone who had spent a lifetime mastering their craft. A shaky or inexperienced hand would leave a chaotic pattern, a telltale sign of a novice. The walls, therefore, are not just a record of how the work was done, but of who was doing it and the sheer level of skill they possessed. To truly understand the effort involved, archaeologists have turned to experimental reconstruction. They have forged bronze chisels and carved dolerite pounders, then put them to the test on actual granite. The results are humbling. Using the Egyptian method, a team of experienced workers might only advance a few millimeters per hour. Shaping a single massive block could take a team of men an entire year. This hands-on research transforms our perspective. It is one thing to read that a process was slow. It is another to feel the vibration of the hammer in your own hands, to see the minuscule amount of rock dust that comes from minutes of exhausting labor. These tool marks are the fingerprints of the ancient world. Each scratch is a testament to patience, each groove a measure of incremental progress. What does a society look like that is willing to invest such time and focus into a single stone? It is a culture that values permanence, that thinks in generations, not years. The quiet, persistent tap, tap, tap of 1,000 hammers was the sound of a civilization building its legacy, one tiny fragment at a time. The silent marks on the quarry walls were not made by ghosts. they were left by the hands of thousands of men and women whose lives were dedicated to the stone. Behind every colossal block we have marveled at stood a community of real people with their own skills, their own hierarchies, and their own daily struggles. For a long time, the popular image was one of endless lines of slaves, whipped into submission to fulfill the ego of a pharaoh. But the archaeological evidence paints a far more complex and human picture. At the worker settlements near the Giza Plateau, excavations have uncovered not squalid slave pits, but organized towns with comfortable barracks, bakeries capable of producing thousands of loaves of bread each day, and hospitals where broken bones were set and healed. These were not disposable laborers, they were a valued, skilled workforce. Inscriptions left by these workers proudly name their crews, titles like the Friends of Khufu or the Drunkards of Menkora, suggesting a team spirit and a shared identity. Their diet was surprisingly robust, with ample evidence of beef, lamb, and fish, proteins that would have been necessary to fuel such physically demanding work. This was not the diet of a mistreated slave, but of a citizen laborer essential to the state's most important project. Far away at Mons Claudianus in the Egyptian desert, the Roman records tell a similar story through administrative papyri and ostraca, the pottery shards used as notepaper. We learn of a blacksmith named Appian who petitions for more tools, and a stonecutter, Ammonios, who is granted leave to visit his family. The workforce was a mix of highly paid, free-skilled artisans and military conscripts, all operating within a strict, almost corporate hierarchy. They were part of a vast, efficient machine, but they were also individuals with names, concerns, and lives beyond the quarry face. So who were they? They were farmers who came to work during the inundation season when the Nile flooded their fields. They were career stonemasons who passed their knowledge from father to son. They were soldiers assigned to engineering duty. The sheer scale of these projects required the mobilization of entire societies, transforming their very structure. A pharaoh's power was measured not just by his army, but by his ability to feed, house, and organize tens of thousands of workers for decades. This human organization was the true foundation of every so-called impossible construction. The great pyramids and temples are not just monuments to kings and gods. They are the collective legacy of the baker, the rope maker, the water carrier, and the stone cutter who left his subtle mark for us to find. They remind us that these wonders were not built on magic, but on the coordinated effort of an entire civilization, a testament to what humanity can achieve when we work together. Moving a 100-ton block of stone across miles of rugged terrain is a problem that would challenge modern engineers, yet ancient cultures solved it with stunning regularity. The solution was not a single secret tool, but a symphony of simple machines and coordinated human effort. The most iconic method was the sledge. Imagine a massive wooden platform carrying a granite giant being pulled along a specially prepared road. But the real trick was not in the pulling, it was in the sliding. Evidence from Egypt shows they likely lubricated these tracks with water or a slurry of wet clay, dramatically reducing friction. A famous wall painting from the tomb of Jehutyhotep illustrates this perfectly. It shows a colossal statue being transported on a sledge, with a worker standing at its base, pouring liquid onto the path directly in front of the runners. This small, simple act could cut the required pulling force by half, turning an impossible drag into a manageable, albeit still monumental, task. Teams of laborers, sometimes numbering in the hundreds, would haul on thick ropes made of papyrus or leather, their efforts coordinated by the rhythmic beats of a drum or the calls of a foreman. Every shout, every pull had to be perfectly synchronized to prevent the sledge from bogging down or, worse, tipping over. For even heavier loads, a different system came into play, the roller. This involved placing a series of logs under the sledge. As the stone moved forward, workers at the back would constantly retrieve the rollers that emerged and rush them to the front, creating a continuous, moving road. It was slow, exhausting work, advancing the stone only a few feet with each grueling cycle. The true scale of this coordination becomes clear with a case like Stonehenge. Some of its smaller bluestones were quarried in the Preseli Hills of Wales, a distance of over 150 miles from the final site. How did Neolithic people achieve this? The journey likely involved a combination of methods. They may have used wooden sledges during overland portions, dragging the stones on a route that followed natural ridges and valleys to avoid the steepest climbs. For river crossings and coastal stretches, they would have built simple but sturdy rafts, lashing the stones to log frames and paddling them along rivers, or even braving short sea voyages, timing their journeys with the seasons to avoid the worst of the winter storms. This was not a haphazard effort. It was a meticulously planned logistical operation requiring an intimate knowledge of the landscape, the rivers, and the materials at hand. Once at the Nile, the challenge transformed. Here, the Egyptians engineered colossal barges from cedar wood, vessels so large they had to be built right next to the quarry to avoid a land journey. A surviving relief from the days of Queen Hatshepsut depicts two massive obelisks being floated down the river on such a barge, with the vessel itself being towed by a fleet of smaller rowboats packed with oarsmen. The mathematics of buoyancy had to be perfectly calculated. A single error in loading could capsize the entire craft, sending a priceless obelisk to the bottom of the river. The success of these transports speaks to a profound, practical understanding of physics. They mastered the principles of friction, leverage, and flotation through observation and experience, not formal equations. But more than that, it reveals a society capable of breathtaking teamwork. This was the ultimate test of ancient project management, a feat of social organization as much as engineering. It required planners to chart the route, foremen to direct the labor, and suppliers to provide food, water, and tools for a small army of workers for months on end. The stone did not move itself. It was moved by the collective will of a civilization, proving that the most powerful force in the ancient world was not magic, but a perfectly coordinated human chain. The placement of these quarries reveals a mind that saw the earth as a living, sacred map. Beyond the practical need for strong stone, ancient architects often selected quarry sites based on profound celestial and geometric principles. What we might dismiss as an industrial pit was for them a sacred intersection between the earth and the cosmos. In the high Andes, the Inca quarried stone from mountains they considered holy, or apus, believing the rock itself was infused with the power of the mountain spirit. The journey from quarry to temple was not just a transport route, it was a spiritual procession, moving sacred essence from one powerful location to another. The alignment of a quarry entrance to catch the first ray of the solstice sun transformed the act of extraction into a ritual, blessing the stone with the sun's power before a single craftsman touched it. This was geology intertwined with cosmology. The very layout of some quarries suggests an advanced use of geometry from the very first cut. Before a single block was freed, the entire site may have been surveyed using ropes knotted at precise intervals to create perfect right angles and alignments. The initial shaping of a massive block was not a rough hacking away of excess stone. It was a careful, calculated process of defining planes and angles according to a preordained sacred proportion, perhaps based on the golden ratio or other mathematical constants found throughout nature. The quarry was the first and most critical stage of construction, where the stone's latent spiritual energy was carefully guided into its intended geometric form. This intellectual framework turns the chaotic landscape of a quarry into a place of deep intention. Consider the mystery of the Moai on Easter Island. The main quarry at Rano Raraku is positioned on the eastern slope of a volcanic crater. Many of the statues, still in their niches, were oriented to face the village complexes below, but their placement within the quarry itself may have held a deeper, celestial significance. Were they positioned to watch the rising of certain stars or the path of the moon across the sky? Similarly, some of the granite quarries in Aswan, Egypt, show alignments that correspond not just to the practical path to the Nile, but to significant solar events. The act of quarrying, therefore, becomes a dialogue with the heavens. It forces us to ask a profound question. Were these sites not just workshops, but open-air temples dedicated to the raw power of the earth and the orderly motion of the stars? The stone they sought was more than a building material. It was a physical bridge between the human world and the divine. A single block of prized granite was more than just a building stone. It was a form of ancient currency, a physical representation of an empire's wealth and reach. The quarries that produced these materials were not silent workshops. They were roaring economic engines, fueling trade networks that stretched for thousands of miles and financing the ambitions of kings and emperors. Control over a source of fine marble or vibrant granite was a direct source of political power. When Rome secured the quarries of Mons Claudianus and Mons porphyrites in Egypt, it was not just acquiring beautiful stone, it was monopolizing the ultimate symbol of imperial authority. The distinctive purple porphyry from these deserts was reserved exclusively for imperial sculptures and monuments, making it physically impossible for a rival to claim the same status. This was economic control as political theater. The very stone used to build a throne room or a triumphal arch sent an unmistakable message of dominance and permanence. The flow of stone dictated the flow of wealth. Vast trade routes emerged, dedicated solely to moving these luxury materials. Egyptian granite traveled by barge down the Nile, across the Mediterranean, and into the heart of Rome. Greek marble from Mount Pentelicus was loaded onto ships and exported across the known world, from the forums of Rome to the temples of Anatolia. This was not a simple barter system. It was a sophisticated industry involving contracts, state-sponsored shipping, and a specialized workforce. Quarrying created entire classes of skilled laborers, from the geologists who identified the best veins to the master carvers who gave the stone its final shape. These were not common laborers. They were highly paid artisans whose expertise was a valuable commodity in itself. The economic ripple effect was immense. A single order for a set of marble columns could employ miners for a year, shipbuilders for a season, sailors for a voyage, and sculptors for a decade. It fed the merchants who supplied the tools, the farmers who fed the workers, and the guards who protected the shipments. The great building projects we admire today were, in essence, massive economic stimulus packages, circulating wealth and stabilizing empires through purposeful employment. How did a block of stone from a remote Egyptian desert end up defining the skyline of a city a continent away? It was the power of an integrated economy, proving that the true foundation of an ancient wonder was not just stone and mortar, but a complex and far-reaching system of trade, labor, and ambition. The scars left by these quarries are far more than historical footnotes. They are a permanent inscription on the planet's surface, a testament to the immense environmental cost of ancient ambition. Every massive stone block extracted required a hidden economy of supporting resources. Vast forests were felled to fuel the fires for smelting metal tools, to forge the countless bronze chisels and iron wedges. Even more timber was consumed in the transport process itself. Think of the immense wooden sledges, the log rollers placed beneath them, and the sturdy barges built to carry stone downriver. The demand for wood was relentless. On Easter Island, this dependency reached a tragic climax. Pollen samples tell a story of a once verdant island covered in a dense palm forest. But as the production of the great Moai intensified, the trees began to vanish. Every statue moved likely required a sledge and rollers made from these very palms. The society was caught in a devastating feedback loop, their spiritual ambition literally consuming the ecological foundation beneath their feet. Without trees, the soil eroded. Without timber, they could no longer build fishing canoes to access deep water fish. The very culture that carved giants from the mountain found itself starved and isolated, a stark lesson in how a single-minded pursuit can unravel an entire world. Yet not every civilization followed this path. Some cultures developed methods that we might now call sustainable. The Inca, for instance, demonstrated a remarkable understanding of long-term stability. Their approach to quarrying was often one of careful stewardship rather than outright exploitation. At sites like Cachacota, they quarried stone by following natural fissures in the rock, a technique that minimized waste and unnecessary damage to the mountain. They moved these colossal stones without the wheel or large animals, which meant they did not require vast quantities of timber for rollers or complex machinery. Their primary tools were stone hammers and bronze chisels, materials that could be sourced and recycled locally. This resulted in a far lighter environmental footprint. The contrast is profound. On one hand, you have the exploitative model that prioritized immediate monumental achievement over ecological balance. On the other, a model that integrated quarrying into the landscape, treating the mountain as a living partner rather than a mere resource to be plundered. This divergence in philosophy determined the fate of civilizations. The choices these ancient engineers made, whether to work with their environment or against it, decided whether their societies would endure for centuries or crumble within generations. This ancient dynamic holds up a mirror to our modern world. We face the same fundamental challenge, just on a global scale. Our own monumental projects, from sprawling cities to immense industries, consume resources at an even more breathtaking pace. The quarries of the past are a powerful cautionary tale written in stone and soil. They ask us a direct and uncomfortable question. Are we, like the builders of the Moai, on a path where our ambition outstrips our resources? Or can we learn from the Inca and find a way to build our future in harmony with the planet that sustains us? The answer is being written now, not in granite, but in the choices we make every single day. The story of stone does not end with the pharaohs or the Inca. It resurfaces in the sweltering heat of 20th century Florida, where a single man performed a feat that seems to defy every known law of construction. Edward Leedskalnin, a frail Latvian immigrant standing just 5 feet tall and weighing barely 100 pounds, single-handedly built what he called the Coral Castle. Working mostly at night to shield his methods from prying eyes, he quarried, carved, and positioned over 1,000 tons of massive coral rock blocks. The result is a sprawling complex of towering obelisks, massive rocking chairs that move with a gentle push, a 9-ton gate that swings open with the touch of a finger, and a perfectly accurate sundial. All of it was accomplished by one man, with no modern machinery, no large teams of workers, and no visible source of power. When asked how he managed it, Leedskalnin would offer only a cryptic smile and a simple explanation. He claimed he had rediscovered the building secret of the ancient pyramid builders, a profound understanding of the laws of weight and leverage. He spoke of understanding the secrets of magnetism and the patterns of celestial energy. He even wrote pamphlets detailing his theories on the relationship between electricity, magnetism, and the endless cycle of life. Witnesses who claimed to have glimpsed his work reported seeing him arranging the massive blocks as if they were mere balloons, humming and gently manipulating them into place. These accounts, though unverified, fueled rampant speculation that he had somehow mastered anti-gravity or tapped into the Earth's magnetic fields. Mainstream science, of course, offers more grounded theories. Engineers suggest he might have used an ingenious system of block and tackle, tripods and chain hoists, leveraging the principles of the fulcrum and counterweight to an extreme degree. He could have painstakingly built earthen ramps, using old truck axles and parts as primitive winches, yet even these plausible explanations strain under the weight of the evidence. How did one man, without formal education or significant funds, possess the engineering genius to move a 9-ton gate with such perfect balance that it pivots on a single, ungreased metal rod? The Coral Castle stands as a powerful, modern anomaly. It is a living monument that directly challenges our assumptions about the past. If one man in the modern era could achieve this with a rediscovered secret, does it not make the accomplishments of entire ancient civilizations seem suddenly more plausible? Perhaps the knowledge was never truly lost, merely forgotten, waiting to be stumbled upon by a determined, eccentric individual. Edward Leedskalnin's lifework forces a humbling question. What if the true secret to moving mountains was not brute force, but a simple, elegant principle of physics that we have yet to fully grasp? Listen closely to the stones of the hypogeum of Hal Saflieni in Malta. In its dark, subterranean chambers, a spoken word can resonate with an unearthly clarity, vibrating through the very rock as if the earth itself is amplifying the sound. This is not a random accident of architecture. It is the signature of a forgotten science, one where the line between building material and musical instrument was utterly blurred. Researchers are now uncovering evidence that ancient cultures did not just see stone for its strength or beauty. They listened to it. They selected specific rocks from the quarry based on their acoustic properties, seeking out stones that could sing. At sites like Stonehenge, certain bluestones produce a distinctive metallic ring when struck, a property that would have been impossible to ignore. These rocks are essentially natural lithophones or stone gongs. Imagine a ritual in that ancient circle where a priest or shaman strikes a towering slab and a deep, resonant tone washes over the participants, a vibration felt in the bones as much as heard by the ears. This sonic dimension transforms our understanding of these places. They were not silent, static monuments. They were dynamic instruments designed to alter human consciousness. The very act of quarrying might have involved this auditory sensitivity. Before a block was ever cut, a master builder could have tapped the living rock face, listening for the purest tone that indicated a dense, flawless internal structure with no hidden cracks or weaknesses. The best building stone was also the best sounding stone. This holistic knowledge represents a profound union of practical engineering and spiritual practice. To shape a block that would later resonate at a specific frequency required an intimate connection with the material, a dialogue that went far beyond simple measurement. Modern experiments have demonstrated the powerful effects of these resonant frequencies. Sound waves at certain low hertz can induce states of deep meditation, alter brainwave patterns, and even create sensations of transcendence. In the echoing chambers of a pyramid or a hypogeum, the collective chanting of voices could have generated a standing wave, enveloping everyone in a blanket of vibration that felt divine. This was not magic but applied physics, a sophisticated manipulation of the environment to serve a cultural and spiritual need. So we are left with a haunting question. Did the ancient engineer, with hammer in hand, close his eyes to better hear the ring of the stone, searching for the perfect note that would make a temple not just stand but hum with life? The quarries hold this secret too, a silent score waiting for the right touch to bring its music back. The words we use to build our arguments were first forged in the dust of ancient quarries. Our modern vocabulary is a living archive of this stoneworking past. Take the word quarry itself. It comes from the Latin word quadraria, which simply means a place where squared stones are cut. Before it meant a hunt for prey, a quarry was a hunt for perfect blocks. A mason was not just a craftsman. The term descends from an old French word for someone who lives in a place, a maker of dwellings, a builder of community. Even the word foundation, so critical to our ideas of institutions and societies, finds its root in the Latin verb fundere, meaning to lay a base for, to make firm. The very concept of laying a foundation is a direct metaphor from the physical act of setting the first, unshakable stone upon which everything else will rise. This linguistic legacy runs far deeper than a few job titles. The entire framework of precision and stability that underpins our laws and sciences was carved from stone. Think about the principles of geometry. The name gives it away, geo for earth, metron for measure. It was literally the science of measuring the land, born from the necessity to survey quarry sites and plot the dimensions of massive blocks. The idea of a standard, an unchanging unit of measurement, was vital for ensuring that stones cut miles apart would fit together perfectly upon arrival. This demand for exactness, for things to be true and square, migrated from the stoneyard into the courtroom, giving us concepts like a standard of evidence or the cornerstone of a legal argument. Our most profound abstractions about society are built upon this stony logic. We speak of building a civilization, of laying the groundwork for peace, of the bedrock principles of democracy. These are not accidental phrases. They are the intellectual inheritance of a world where human ambition was measured in the movement of mountains. When a philosopher spoke of a society built on a solid foundation, every listener understood the metaphor instinctively. They lived in a world of temples and walls that had stood for 1,000 years. They knew that a weak foundation meant collapse. The physical reality of quarrying and construction provided the only durable analogy for creating something meant to last forever. This journey from physical rock to abstract thought reveals a stunning truth. The act of shaping granite and limestone did more than create monuments. It fundamentally shaped the human mind. It taught us the value of patience, the necessity of precision, and the meaning of permanence. The quiet, persistent tap of a mason's hammer did not just square a block. It helped to square our very understanding of the world. How else could we conceive of truth, if not as something solid and unyielding? How else could we imagine justice, if not as a structure built to withstand the storms of time? The quarries gave us more than stone. They gave us the language to build our world, both in rock and in thought. A master stonecutter from the high Andes and another from the sun-drenched hills of Greece, separated by thousands of miles and as many years, would have recognized each other's work instantly. Their shared language was not spoken but carved into stone. The polygonal masonry of the Inca, with its complex, interlocking blocks shaped like a three-dimensional puzzle, finds a startling mirror in the cyclopean walls of Mycenaean Greece. At sites like Sacsayhuaman in Peru and the Lion Gate in Mycenae, the stones fit with such uncanny precision that the joins defy detection. Neither culture had contact with the other, and yet they arrived at the same brilliant, labor-intensive solution. They understood that a wall built from uniquely shaped, tightly fitted blocks would be far more resilient to earthquakes than one made of uniform rectangles. When the ground shook, these stones would shift and settle, locking themselves tighter rather than collapsing. This was not a shared blueprint, but a shared logic, born from confronting the same relentless forces of nature. The same pattern of independent invention appears with the most fundamental tools of moving stone. The lever, the ramp, and the roller were discovered again and again across the globe. Egyptian tomb paintings depict the use of levers to position fine masonry, just as the builders of Stonehenge likely used timber poles to heave their massive sarsens into place. The concept of the inclined ramp is documented in the ruins of Mesopotamian ziggurats, theorized for the Great Pyramids of Egypt, and physically evidenced in the earthen spirals leading up to ancient mounds in North America. When a human society needs to lift something impossibly heavy, the ramp is an almost inevitable conclusion, a simple slope that trades a brutal vertical lift for a longer, more manageable incline. Even the method of dressing stone, of shaping its final surface, converges. The practice of pounding a rock face with a harder stone to create a flat, dimpled surface appears in both the granite quarries of Aswan and on some of the most ancient structures in Japan. So how do we explain this global echo? One possibility is the slow, meandering path of cultural diffusion, where a core idea traveled along ancient trade routes, adapting and evolving with each new culture it touched. Yet for many of these parallels, the distances in time and space are simply too vast for this to be a comfortable explanation. The more profound possibility is that these techniques are not inventions in the traditional sense, but discoveries. They are latent solutions waiting within the problems themselves. When 100 people are separately presented with the same massive block of stone and told to move it, a certain percentage will inevitably discover the principle of the lever. Another group will figure out that rolling it on logs reduces friction. Human ingenuity, when faced with a universal physical challenge, appears to funnel toward a set of universal physical solutions. This convergence speaks to something fundamental about the human mind. It suggests that our problem-solving logic is wired into the fabric of the material world. We are all reading from the same cosmic instruction manual written in the laws of physics. The isolated cultures that built these wonders were not sharing secrets. They were each having the same silent conversation with stone, and the stone, it seems, gave them all the same answers. The most solid rock can be conquered by the simplest of elements. Water, the very essence of life, was also one of the ancient world's most powerful engineering tools. Its role in the quarries went far beyond just quenching the thirst of workers. It was a cutting agent, a lubricant, and a precision instrument, all in one. The most dramatic application was in splitting massive blocks from the living bedrock. Workers would meticulously drill a line of holes along the intended fracture line. Into these holes they hammered dry wooden wedges, then they poured water over them. As the wood absorbed the moisture, it expanded with a force so immense it could cleanly shear through tons of granite or limestone. This method, perfected by the Romans in their Egyptian quarries, allowed for surgical precision, creating perfectly flat planes on stones that would become the columns of the Pantheon. But water's work was not done once the block was freed. Moving a 200-ton sledge across the desert sand was an exercise in defeating friction. The solution was elegantly simple. A worker would walk ahead of the sledge, pouring water or a slick slurry of wet clay onto the pathway. This transformed the dry, gritty surface into a slick, muddy track, reducing the pulling force required by more than half. Wall paintings from Egypt immortalize this very act, a testament to its fundamental importance. Water also played a vital role in the finer work of drilling and carving. For drilling deep holes or shaping intricate details, workers used a tubular drill, often a hollow reed or copper pipe. They would spin this drill back and forth while feeding a slurry of wet sand and water into the cut. The sand, harder than most quarry stones, acted as the abrasive, while the water both cooled the drill bit and carried away the ground rock particles, keeping the cut clean and efficient. This simple mixture of sand and water could, with patient, persistent motion, bore through the hardest granite. The evidence of this sophisticated water management is still etched into the landscape around ancient quarries. At sites like Mons Claudianus, you can find the remains of elaborate systems of stone-lined channels, cisterns carved into the bedrock to capture precious rainfall, and even small dams to control seasonal floods. This was not a haphazard collection of puddles. It was a deliberate, engineered network designed to capture, store, and direct water exactly where and when it was needed. This mastery of a simple liquid reveals a profound intelligence. These engineers understood the fundamental physics of expansion, lubrication, and abrasion on an intuitive level. They saw water not just as a resource, but as a willing partner in their ambition. How did they manage to manipulate the most solid material on Earth? They did it by commanding the most fluid one, proving that true power lies not in fighting nature, but in understanding its gentle, relentless force. An abandoned quarry is more than a deserted pit. It is a time capsule, a moment of immense ambition frozen in its tracks. While we marvel at the finished temples and towering statues, it is these half-carved sites that whisper the most honest truths about the ancient world. They show us the process, not just the product. In the silent chaos of an abandoned worksite, we find the tools left where they fell, the outlines of workers' huts, and the massive blocks forever waiting for their journey to begin. Each of these elements is a clue to a story that was never finished. The most famous of these frozen moments is the Unfinished Obelisk in Aswan. Lying in its granite bed, it is a masterclass in ancient Egyptian engineering, revealing every step from the initial layout to the final undercutting. The tool marks are a permanent record of the pounding rhythm of dolerite hammers. But then we see the crack, that single, fatal flaw in the stone that forced the architects to walk away, a testament to the immense gamble of working with such colossal monoliths. A single imperfection hidden deep within the bedrock could undo years of backbreaking labor. Across the world, the quarry at Rano Raraku on Easter Island presents a different kind of abandonment. Here, it was not a cracked stone that halted work, but a collapsing society. Nearly 400 Moai stand in various states of completion, some mere faces emerging from the cliff, others fully carved but never freed. The scene is hauntingly still, as if the workers simply put down their basalt picks one day and never returned. The evidence suggests a society that reached its breaking point, where the spiritual drive to carve giants was finally overwhelmed by ecological reality. The trees were gone, the soil was depleted, and the very act of creation had consumed the means of survival. These sites force us to confront the immense pressures behind these megaprojects. A sudden political shift, like the death of a pharaoh, could redirect all labor and resources to a new tomb or temple overnight. An economic crisis, a war, or a prolonged drought could drain the treasury and scatter the workforce. The stones themselves bear witness to these crises. A half-cut block shows the precise technique, but its abandonment tells a story of a kingdom in turmoil. What can we learn from these failures? They teach us that these monumental achievements were never inevitable. They were the result of a fragile alignment of political will, economic surplus, and environmental stability. When that balance was lost, the hammers fell silent. These quarries are the archaeological equivalent of a paused film, allowing us to study the frame-by-frame process of building the impossible. They remind us that history is not just a record of what was completed, but also a poignant archive of what was dreamed, attempted, and ultimately left behind in the stone. But what if the stones themselves are lying to us? A radical idea from materials scientist Joseph Davidovits proposes that the Great Pyramid's massive blocks were not cut and dragged into place, but poured. This is the geopolymer theory, suggesting the ancient Egyptians invented a form of synthetic stone, an ancient concrete mixed and cast directly on the pyramid's rising tiers. The evidence comes from a microscopic level. Analysis of stone samples from the Giza pyramids reportedly shows mineral compositions that do not perfectly match the limestone from the known quarries across the Nile. Proponents point to the presence of air bubbles and what looks like organic material, possibly hair or plant fibers, trapped within the stone, which they argue would be natural inclusions in a man-made slurry mixture. The theory also offers an elegant solution to some of the pyramid's most perplexing logistical puzzles. It would explain the superhuman precision of the blocks, many fitting together with seams thinner than a credit card, with no visible chisel marks. If the limestone was crushed, mixed with a reactive binder like natron salt, and then poured into wooden molds, it would create a perfect custom-fit block every single time. This method would eliminate the need to move thousands of multi-ton stones, replacing back-breaking transport with clever chemistry. The quarries in this scenario would not be sources of finished blocks, but massive pits where raw limestone was mined and crushed into powder. It completely redefines the very meaning of the word quarry. Yet, the majority of Egyptologists and geologists remain deeply skeptical. They argue that the geological match between the pyramid stones and the Tura and Mokattam quarries is in fact quite strong. They point to the overwhelming physical evidence at those quarries, including the clear tool marks left on the bedrock and the discovery of partially extracted blocks that were clearly being cut, not cast. The presence of organic material, they counter, could be contamination from thousands of years of exposure or from the modern sampling process itself. The debate is far more than an academic disagreement. It strikes at the heart of how we perceive ancient innovation. Were the pyramid builders primarily masters of logistics and brute force, or were they also brilliant chemists who manipulated matter on a grand scale? The geopolymer controversy forces a humbling question. Could the most iconic symbol of carved stone in human history actually be the world's oldest and most magnificent concrete pour? The answer remains locked within the chemistry of the stones, a recipe we are still trying to decode. Granite was not merely strong. For the ancient Egyptians, its crystalline strength was a physical promise of eternity. They chose this formidable stone for the burial chambers deep within their pyramids, the very heart of a pharaoh's tomb, because they believed its resilience would protect the king's spirit for millions of years. It was the bone of the earth, meant to last as long as the soul itself. In stark contrast, the gleaming white limestone that once encased the Great Pyramid was selected for an entirely different symbolic purpose. This bright stone, quarried from across the Nile, was meant to reflect the blazing sun, transforming the pyramid into a colossal beacon of pure, divine light. It connected the earthly structure to the celestial realm, a ramp of light for the pharaoh's ascent. This symbolic language of stone echoes across the world. Far across the Atlantic, the Olmecs and Maya of Mesoamerica sought out a different kind of power. They prized jade and greenstone not for their structural strength, but for their vibrant color, the deep green of lush vegetation and flowing water. In a world dependent on maize and rain, these stones embodied life, fertility, and the very breath of the wind god. A jade mask placed on a ruler's face was not simple decoration. It was a spiritual transaction, a way of infusing the leader with the vital, life-giving forces of nature itself. The stone itself was considered alive, holding a soul force that could be communicated with and harnessed. This profound symbolism dictated every aspect of construction, from the quarry to the final placement. A temple dedicated to a water deity might be built from a stone veined with patterns that resembled flowing rivers. A tomb designed for eternity would use the most imperishable rock available, a deliberate statement against the decay of the mortal body. The choice of material was the first line of a sacred text, written not on papyrus but in the very fabric of the building. So when we look at these ancient structures, we must learn to see more than just shaped rock. We are looking at a coded language of belief. What did it mean to a culture to build their most sacred space from a mountain they considered a living god? The stone was never silent. It was chosen to speak, to radiate meaning, and to last long enough for its message to cross the centuries to us. A perfect stone wall tells only half the story. The true measure of ancient engineering lies not just in what survived, but in what cracked, settled, or was left forever unfinished. These failures are our most honest teachers, revealing the outer limits of knowledge and the immense risks these builders took. At the Temple of Apollo in Didyma, in modern-day Turkey, the scale of ambition outstripped even Roman capabilities. The temple's courtyard was meant to be flanked by 3 towering, fluted columns, each carved from a single piece of marble. 3 of these colossal drums still lie in the ruins today, never raised into position. They are so massive that the grooves for the fluting were carved before they were lifted, a calculated risk that presumed they could be hoisted. They never were. The engineering required to lift such weight, perhaps using a complex system of winches and cranes, either failed or was deemed too perilous to attempt. The site became a monument to a dream that was simply too big, a permanent lesson in the hard realities of gravity and mass. Far across the world, high in the Andes, the builders of Machu Picchu left their own quiet testimony to failure. Scattered around the site are several massive stones, precisely shaped yet never placed in the walls. These were rejects. A skilled Inca stonemason would have inspected each block for hidden fissures or weak grain. A stone that might fracture under stress, or that could not be shaped to interlock perfectly with its neighbors, was simply abandoned. This was not a sign of incompetence, but of supreme quality control. It reveals a society that understood its materials so intimately that it would rather waste months of labor than compromise the structural integrity of a sacred city. This practice of rejection speaks to a sophisticated process of trial and error, where the definition of success was absolute perfection. Every collapse, every cracked lintel, whispers a story of adaptation. When a foundation subsided, they learned to dig deeper, to interlock stones with the bedrock itself. When an arch showed signs of weakness, they thickened the walls or added external buttresses. These were not static traditions handed down from on high. They were living sciences, constantly refined through painful, costly experience. The broken obelisk in Aswan is a masterpiece of engineering, but it is the crack running through it that truly illuminates the process. That single flaw forced a reevaluation, a moment of collective decision-making where the architects had to cut their losses and walk away. What do these abandoned projects teach us? They show that ancient genius was not an innate, magical gift. It was a hard-won wisdom forged in the dust of the quarry and on the crumbling edge of disaster. Their greatest triumphs were built upon a hidden foundation of countless quiet failures. Hidden beneath dense jungle canopies, entire ancient landscapes are now coming into view. LiDAR, or light detection and ranging, is a revolutionary technology that uses laser pulses to map the ground surface, effectively seeing through the thickest vegetation. From an airplane or drone, it scans the terrain, creating a high-resolution, 3-dimensional map of the Earth below the trees. This has revealed sprawling, unknown quarry networks in places like the Maya world, where massive limestone extraction pits and transport causeways were completely invisible to the naked eye. We are discovering that what we thought were isolated temples were actually the endpoints of vast industrial complexes, now reclaimed by the forest. At the same time, ground-penetrating radar sends pulses of energy into the soil, painting a picture of what lies beneath our feet without a single shovel breaking ground. This technology is mapping subterranean tunnels and worker camps, showing us the full scope of daily life in these monumental work sites. We can now locate ancient workshops, tool storage areas, and even the foundations of administrative buildings, giving us an unprecedented understanding of the social structure that powered these operations. Above it all, drones equipped with high-resolution cameras are providing a new perspective on massive quarries. They capture the grand layout of a site like Rano Raraku in a single, breathtaking image, allowing archaeologists to see patterns and relationships between the statues that were impossible to grasp from the ground. This bird's-eye view can reveal the precise sequence of extraction, showing us the order in which the Moai were carved and freed from the rock face. Perhaps the most precise tool, however, comes from the realm of chemistry. Isotopic analysis involves studying the unique chemical fingerprint of a stone. Every quarry has a distinct signature, a blend of trace elements and mineral isotopes that is as unique as a human fingerprint. By taking a tiny sample from a finished stone in a distant temple and comparing it to samples from known quarries, scientists can now pinpoint its exact source with incredible accuracy. This has resolved long-standing debates about ancient trade. We now know, for instance, that some of the blue stones at Stonehenge came from very specific outcrops in Wales, and that Roman marble found in North Africa can be traced directly to quarries in Greece. These tools are not just giving us answers, they are allowing us to ask entirely new questions. Instead of wondering how a stone was moved, we can now ask why it was moved from that particular mountain, from that specific vein. What was so special about that exact piece of the earth? The secrets of impossible construction, locked in stone and soil for millennia, are finally meeting their match in 21st century technology. What undiscovered truths lie just a few feet below the surface, waiting for the right tool to listen? The scattered clues from quarries around the world begin to align, forming a single, coherent picture. We have searched for a magic bullet, a single lost formula that explains everything, but the truth is far more profound. The secret to impossible construction was not one thing. It was the perfect synergy of multiple factors, a grand orchestra where every instrument played a crucial part. Immense manpower was the engine, but it was directed by sophisticated logistics that could plan a project spanning decades. This human power was guided by a deep, empirical knowledge of materials, an intuitive understanding of physics, and a level of skill honed over generations. There is no evidence of a single, universal lost technique, but rather a collection of locally perfected methods, each adapted to the specific stone and landscape. The true magic was not in a chemical elixir or alien intervention. It was in the human capacity for collective, focused effort. Imagine the coordination required. The stonecutters at the quarry face, the rope makers producing miles of cordage, the road builders preparing the transport route, the water carriers sustaining the entire operation, and the cooks feeding thousands. This was not a chaotic mob. It was a society functioning as a single, purposeful organism. The precise tool marks, the abandoned ramps, and the worker settlements all point to this same conclusion. The real secret hidden in the quarries is not a tool or a recipe. It is a blueprint for human collaboration. This synergy transformed staggering ambition into enduring stone. How do we measure such a civilization? Not by the weight of the stones they moved, but by the strength of the social fabric that made it possible. The legacy of the ancients is not just in the monuments that survived, but in the silent, powerful lesson they left behind about what we can achieve when we work together toward a common, monumental